everybody to another video. Today we are going to have the IGCSE chemistry revision notes. So basically, as you can see on my screen, these are the contents for the IGCSE chemistry. In total, there are 22 chapters which are included in the Cambridge Chemistry IGCSE. So in today's video, we'll talk about the first content, which is about the states of matter. There are several videos talking about the several topics that are required or that are needed in the IGCSE syllabus. I will be making on each chapter, so therefore you can revise better, and we are gonna be start today with the first chapter, which is the states of matter, and these are the contents that are included in this chapter. So we have the first content, which is states of matter, second about the kinetic particle theory of matter, and the third is about the mixture of substances and also the diffusion. So we'll in today's lecture, in today's video, we'll discuss all these three contents which are related to the states of matter. So let's start. So first of all, basically you should know about the different states of matter. So there are three states of matter. First one is the solid, second we have the liquid, and third we have the gas. First of all, we'll have the distinguishing properties of the solids, liquids and the gases, and I will first share the structures of the solid, liquid and gases in terms of the particle separation and also the arrangement of the particles that are present between them. As you can see on my screen, this one is the arrangement for the solid particles or for the solid substances that are present there. So this is the structure of the solids or the arrangement of the particles that are present in case of the solids. So in the solids, the particles are very closely packed and they have the fixed arrangement. As you can see here, the substances or the particles that are present in the solid state are closely packed and they have the fixed arrangement. So let's now talk about the arrangement of the particles that are present in the liquids. So these are the particles or the substances that are present in the liquids, and liquids are closer together but they have a random motion, as you can see on my screen. So next, the third one, we'll talk about the gas. These are the gas molecules or gas particles that are present here, and I will describe you the arrangement of the particles, the separation and also the motion of the particles that are present here. Gas particles are spread apart. There is more distance between the gas particles as compared to the liquid and the solid ones, and they also have the random motion. So both the liquids and the gases have the random motion but not the solids. Solids have fixed arrangement. They have fixed arrangement. So these are the properties that we'll discuss today about the solid, liquid and the gases. So next we'll discuss about the separation and also the motion of the particles, solids. Now let's change the color. So first we'll discuss about the solids. So solids have fixed and regular arrangement of the particles. They are regular and the particles that are present here have regular arrangement, and the particles just vibrate that are present at their fixed positions. They only vibrate at their fixed positions. They cannot be compressed, and these are the important properties related to the solid. Next we'll discuss about the liquid. So for the liquids, they are randomly packed or random arrangement is present between the liquid particles, and these particles can be able to move or pass each other, and they can take the shape of any container which will add them, and they cannot be compressed. Liquids cannot be compressed, solids and liquids both cannot be compressed. So these are the important properties that are present in case of solids, liquids, and the next liquids are closer together and they also have the random arrangement. So next, the third one, the third state of matter, that is the gases. And in case of gases, particles are arranged randomly and they have the most energy. That's why the particles in the gas are relatively spread out, as you can see in the structure of the arrangement of the particles, and they spread out more and move randomly in the directions, and they can be compressed. They can be compressed, they have random arrangement, right, and they can be spread more. This because of the properties of the particles that are present in case of gases. So these are the important properties related to the solid, liquid, and gases. This is the most basic one, and next we'll talk or discuss about the change of state in terms of the melting, boiling, freezing, and also the condensing. So the next one is about the change of state. Change of state. In case of change of state, we have different physical properties that are included in it, like the physical changes, melting, boiling, evaporation, freezing, and condensation. All are included into the change of state or change of phase. For example, we have solid substances, and then we have liquid, and we have gas. Gas particles are present there. So how can we express them, or how can we say about the different states or change of state in terms of the melting, boiling, evaporation, freezing, and condenses? So first of all, we'll talk about the physical changes that involve the forces that are present between the particles of the substances. If we talk about the melting, melting is just like that if it changes from the solid to the liquid. When a substance changes its state from the solid towards the liquid, we call it as melting. So this one is the melting, and when the substance changes from the liquid towards the gas, we call it as evaporation. So when the particles will move from liquid to a gas state, we call it as evaporation, and from solid to the liquid, it is known as melting. And if we talk about the reverse, like if the particles change from gas state towards the liquid, we call it as condensation, and from liquid towards the solid, we call it as freezing. So this one is the freezing, and from gas towards the liquid, we call it as condensation. So kinetic particle theory model discuss all the three states of matter by presenting the particles as the small solid spheres, as I already told you or explained you in terms of the melting, boiling, freezing, and condensing the particles. And if we talk about the melting, melting is the change of the state from the solid towards the liquid, and boiling or evaporation is the change of state from the liquid towards the gas. Bubbles of the gas will form throughout the liquid, rising to the surface and to evaporate into the surrounding. Evaporation is also just like the boiling, but there is one difference between the evaporation and boiling, is that boiling, anything or any substance boils at a specific temperature, and if we talk about the evaporation, evaporation can happen almost at all the temperatures, right? And next, if we talk about the freezing, freezing is the conversion of the state from the liquid towards the solid, and condensation is this change of state from the gas to the liquid. When a solid substance changes into a gas phase, directly into the gas phase without converting into the liquid, we call it as sublimation. This is also another state which we call it as sublimation, and in sublimation the particles directly converted from the solid to the gas state without converting into the liquid one. So that is known as the sublimation. And if we talk about the temperature change, melting and freezing take place at the melting point, boiling and condensation take place at the boiling point. So when temperature increases, temperature will increase when the substance is converting from the solid towards the gaseous phase, then the temperature increases. Steam or gas particles have more temperature and solid particles have less temperature. For example, if I gave you the example of ice and steam, and the example of liquid is water, H2O, that is the formula of water. So ice has the temperature may be like 0 degrees Celsius, that is also the freezing point of the water and the melting point of the water. Steam has temperature more than 100 degrees Celsius, and the normal liquid water that is present in the room temperature has a temperature of 20 to 25 degrees Celsius. So if we move from the solid state towards the gaseous phase, the temperature increases, and if we talk about the reverse, from the gas towards the solid state, then the temperature decreases. So these are the effects of the temperature on the conversion of the state or the change of state. As the temperature increases, the volume of gas also increases, and as the pressure increases, then the volume of gas will decrease, and if the pressure decreases, then the volume of gas will increase. So these are the effects of the temperature and pressure on the volume of the gas. I will explain this to you. When the temperature increases, if we increase the temperature, if this one is the container in which we have any type of gas particles, when the temperature increases, then what will happen? The volume of the gas will increases. Just because of that, the gas particles expand just because of the heating. And as the pressure increases, when we increase the pressure, when we apply the pressure to a container like this, these are the gas particles that are present here, and from the top we apply the pressure, and when we apply the pressure, what will happen? The volume will decrease. The volume of the gas will decrease because of the applied pressure from the top. But if we decrease the pressure, like now the pressure is here, so then the volume increases, as you can see here on my screen. In the first one, this is the first one, in the first picture, and in the second picture, pressure increases in the first and pressure decreases into the second, as you can see the position or direction of the arrow on my screen. So this is about the changes of state in terms of the kinetic particle theory, and also the effect of temperature and pressure on the volume of the gas. Now we'll discuss about more about the kinetic particle theory model that describes the three states of matter by presenting the particles as the solid, liquid, or the gases. So you can see here, these are the arrangement of the particles that are present in the solid, liquid, and in the gases. For the melting, boiling, and evaporation, thermal energy must be transferred into the kinetic energy in the particles so that they gain enough energy to overcome the intermolecular forces. So the forces of attraction between the solid particles are overcome through the melting, and the liquid particles must be able to spread apart and move around. For freezing and condensation, energy is lost from the particles in the substance, and the intermolecular forces are also formed between the particles that form the particles or hold the particles closer together. So next we'll discuss about this is all about the kinetic molecular theory. There are some important points related to this theory. The more the particles have kinetic energy, the more movement they have, which will cause a change of state from the solid towards the liquid, and from the liquid towards the gaseous phase when they have more kinetic energy. Because of the movement or the arrangement of the particles, the more movement they have, the more change of state they will form. Okay, so this is about the kinetic molecular theory, and next we will discuss about the heating and cooling curves. One thing I want to tell you that the one which we discussed before the kinetic particle theory, all are included in the core, and the next which I am discussing about the kinetic molecular theory or change of state in terms of the kinetic particular theory, and also the interpretation that is included only in the extended one. So now we will discuss about the heating and cooling curves, or the interpretation of the heating and cooling curves. So now, before going towards the interpretation of the heating and the cooling curves, I think you should know about the change of state, the interconvariance between the changes of state. So the first one which we will discuss today is the melting, which we also discussed here. So melting is the change of state from the solid towards the liquid. From the solid towards the liquid is the change of state, and we call it as melting. Melting requires heat energy, which transforms it into the kinetic energy and also allow the particles to move. When the particles move, then they will start towards the melting process, and that occurs at the specific temperature, which is known as the melting point of any substance. So there is a specific melting point of any substance of the pure. If the substance is pure, then the melting point is specific. For example, the melting point of water, the melting point of pure water is 100 degrees Celsius. So the melting point of water is 0 degrees Celsius, which is the specific of the pure water. If is there any impurity that is present in the water, then the boiling point raises of any substance. Like maybe the boiling point raises and the melting point decreases if there is any impurity that is present into the any substance. Like for example, if there is any impurity that is present in the water, then the melting point decreases and the boiling point raises. Like boiling point maybe increases up to 105 110 degrees Celsius, and the melting point decreases just like the melting point of water is 0 degrees Celsius. So next is the freezing. Freezing is the state of matter freezing. Next one is freezing. Freezing is the state when a liquid changes into a solid. When the liquid changes into a solid, we call it as freezing, and the freezing point is the reverse of the melting and occurs at exactly the same temperature as the melting. Hence the melting point and the freezing point of the pure substances are same. For example, water freezes and melts at 0 degree Celsius, and it requires a significant decrease in temperature or loss of thermal energy from any substance and occurs at a specific temperature. So this is all about the melting and the freezing point, and next we'll discuss about the boiling point. Boiling point is when a liquid changes into a gas. It is the conversion of state from the liquid towards the gas, and it requires heat energy, as I told you in the freezing, that in freezing is when the liquid changes into a solid, and this requires a decrease in temperature. But in case of boiling, there should be an increase in temperature, and which causes the bubbles of the gas to form below the surface of the liquid, and also allow for the particles or liquid particles to escape from the surface of the liquid and within the liquid. So it occurs at a specific temperature, which we call it as boiling point, and boiling point of water is 100 degrees Celsius. If is there any impurity that is present in the water, then the boiling point increases or raises above the 100 degrees Celsius if the water is impure. Next, evaporation. Evaporation is just like boiling, but there is one significant difference between the evaporation and the boiling. Evaporation occurs when a liquid changes into a gas and occurs over a wide range of temperatures, but boiling occurs at a specific temperature. That is the basic difference between these two terms. Next, the last one which we talk about, which one is condensation. And in case of condensation, there is a change of state from the gas into the liquid. From gas to the liquid. This one is the change of state, and the condensation takes place over a range of temperatures. When a gas is cooled, its particles lose energy, and when they are bumped into each other, they lack the energy to bounce away again. Instead, they group together to form the liquid. So this one is all about the change of state or the interconversion of the states. So let's talk about now the interpretation of the heating and the cooling curves, and this one is for the extended only. When the substances are heated, the particles absorb thermal energy, which is converted into the kinetic energy, and this is the basis of the kinetic particular theory of matter. Kinetic particular theory, let me change the color. Kinetic theory of matter. So in kinetic theory of matter, the main basis is about when the substances are heated, the particles absorb thermal energy, which is converted into the kinetic energy, and this is only the basis of this kinetic particular theory. Heating a solid will cause the particles to vibrate more as the temperature increases, and the particles vibrate so much that the solid expands until the structure breaks. So this is when a solid is melted into the liquid form. So we will talk about the changes that happen here in the heating curve through a graph. Let me draw this one. So this is the graph. As you can see on my screen, the temperature versus the time graph. So here is the 0 degrees Celsius, 0 degrees Celsius temperature, and when the substances are heated, the particles absorb thermal energy, which is converted into a kinetic energy, and this is the basis. And heating a solid will cause its particles to vibrate more, and the temperature will increases, the particles vibrate more. During the change in state, what happens when we heat the ice is a form of solid, so when we heat them, what will happen? They will change in the state. When the ice is heated, energy is given for warming up the particles of the ice, and they vibrate more, and the expansion will happen here. So this is, you can see here, this line shows the solid that is present there. The solid particles are there, and these are the solid particles, and they are warming up, and when they warmed up, what will happen? The solid is converted into the liquid state. So this one on the graph, you can see here, this is the point of the melting, and now we have the solid plus liquid substances that are present at this melting point. So what happens when we increase the temperature more? During a change in state, there is no increase in temperature, no temperature change will happen, like I will show you this one. During a change in temperature here, during a change in state, no temperature change will happen during this phase. No temperature change will happen during a state. There is no temperature change during this state. Why? Just because of that the substances are changing their state. Substances are changing from the liquid towards the gaseous, or maybe from the solid towards the liquid state. So during a change in state, there is no temperature change. So at this point, we have the liquid particles. All the liquid particles are present here, but what happens again? You can see here, this next we have the evaporation or vaporization that will happen here. Water is warming up, increase in temperature, particles will give enough energy to escape, and then they form the gas. So at this point, we have the liquid plus the gas particles at this point. And then what will happen? Evaporation will occur. When evaporation will occur, all the water will be converted into the steam or the gas phase, and this will show the steam or the gas, this one. So first I will show you, or we will include this, or we can do. So here we will divide the graph into the different segments. For example, from here we start. This is the first A, second this one is the B, and third this one is the C section, and now we have the D section. Next we have E, and in the last we have F. So now I will explain you about all these points in which we divided our graph. So first of all, in A to B, what will happen? Energy is given to the particles for the warming up. Energy is given and particles warming up and they vibrate. Energy is given, particles vibrate. Just because of that, they are in solid state. When we give heat energy to them, what will happen? They convert the thermal energy into the kinetic energy and particles vibrate more, and then expansion happens. They expand. So this is about between the A to B state, and next we will move towards the second one, which is from B to C. What happens here? Melting happens here. Melting, you can say that heating a solid will cause the particles to vibrate more. As the temperature increases, the particles vibrate so that the solid expands until the structure breaks. This is when the solid melts. So in the B to C portion, the solid melts into a liquid. So after that, heating a liquid will cause the particles to move. In C to D, what will happen when we heat a liquid will cause the particles to move more and they spread out. Some of the particles will gain sufficient energy to overcome the intermolecular forces. This is when the liquid starts to evaporate. And from in the point C to D, water is warming up again, and particles will have enough energy to escape to the gas. Next, from D to E, what will happen? Evaporation or boiling will happen here, and this one is also the boiling point of the water from D to E. Next, E to F, we have the steam, that is the gas phase or steam is present there, and when the boiling point is reached, all the particles will gain enough energy to escape and the liquid boils into a gas. So these changes in state can be shown here in the graph, and this one is known as the heating curve of the graph. Heating curve show the states change in state and also the temperatures change as the time passes. So this one is the heating curve, or the interpretation of the kinetic molecular theory through the heating curve. As you can see here, we divided the graph into the different segments: A to B, B to C, C to D, and D to E, or last where we have the F. F is the final stage or the final last one. So this one is the temperature. As you can see here, I will show you here the boiling point of the water, which is 100 degrees Celsius, and this one is the boiling point. This is the boiling point of the water, which is 100 degrees Celsius, where water boils, or where water is converted from the liquid to the gaseous phase. So this one is the heating curve, and next we'll move towards the cooling curve. Next we'll move towards the cooling curve. Cooling curve is just like the heating curve, but there is one difference between them. It is opposite to the heating curve, and you can say that but it's like the mirror image of the heating curve. So first I will show you the change in state, the temperature effect, or the change of state between the cooling curves and the heating curves. And you can see here, first of all we'll draw the graph of the cooling curve. In the graph we have again same temperature and time graph, temperature versus the time. But there is one difference now between the cooling curve is that now we have the gaseous phase first, and we cool the gaseous phase or steam anything. You have the gas phase, steam phase, which you cool down, and it will be like this one. So now gas has the more temperature or the higher temperature as compared to the solid. So at this point we have the gaseous phase. So this one is the gas. When the temperature decreases, then the gas particles cool down and they become condensed and convert into the liquid. So this is the point at which we have the gas plus liquid particles, and this one is known as the condensation, or we can say that our substance or the gas particles will start condensing. They start condensing and they convert into the from gas towards the liquid phase. So this one is the time or at which there is no change in temperature. Why there is no change in temperature? Just because of that all the particles are converted into this one. As I show you here, this one is also no change in temperature. Why there is no change in temperature at this point? Just because of that during a change in state there is no change in temperature, because the particles are converting from the solid into the liquid and from liquid into the gas phase. So that's why we draw the straight line on our graph. Now we have the cooling curves, and in the cooling curves it's just like the mirror image of the heating curve, and cooling curve is like the particles of the gas are moving more and they cool down. When they cool down, particles of the gas are converting into the liquid and they condense. When they condense, they form a liquid. So this one is the liquid. Next, when we give or if there is a decrease in temperature, these liquid particles will start converting into the solid. That is known as the freezing. So this one is the freezing, and at this point we have the liquid and the solid particles that are present here, and now there is no increase in temperature. There is no temperature change. As you can see here I draw just the straight line that shows that there is no change in temperature during a change in state, because at this point we have both the liquid and the solid particles. After the liquid and the solid particles, they are converted into all the liquid and solid particles are converted into solid, like this one. So at this point now we have all the particles are converted into the solid state, and the horizontal sections occur where there is a change of state but there is no change in temperature. Heating and cooling curves are used to show how changes in temperature affect the change of state. So this one is all about the cooling and the heating curves. So cooling curve is just like the graph that shows the temperature against the time as the gases cool to a liquid to a solid phase. I'm concluding all this. At the start of the graph you can see here the substance is still in the gaseous phase, but when the temperature decreases as the energy is lost, at this point I'm talking about this point. As the energy is lost into the surroundings, the temperature decreases as the energy is lost, and then the line becomes straight. New bonds are formed between the gas particles, turning them into the liquid through the condensation. So this one is the point of condensing a liquid. And then the temperature decreases further as soon as all the gas particles have turned into the liquid. So the line becomes horizontal again. Why the line becomes horizontal again? Just because of that the freezing point is reached and more bonds are formed that will change the liquid to a solid state. So this one is the cooling curve, and this is the condensation point. I will show you. This one is the condensation point, or this one is the freezing point of any liquid. So this is all about the heating and the cooling curves. So now we will discuss about the pressure and the temperature that is present in the gases. This one is the next topic that extends in the kinetic molecular theory. In terms of the kinetic particle theory or molecular theory, the particles are the effects of the temperature and the pressure on the volume of the gas. The effect of temperature and pressure will be discussed in this. A change in temperature or the pressure will affect the volume of the gases. For example, as the air inside a hot air balloon is heated up, it expands and the balloon gets bigger. Maybe you observed about this one. This is just because of the volume of the gas that increases. Suppose this one is the hot air balloon, and in this hot air balloon, what happened? An increase in temperature or change in temperature, or if it is heated up, it expands and the balloon gets bigger when it heats up. So by heating it, the balloon gets bigger. This is because the volume of the gas increases, and when the volume increases, the volume of the gas increases, and when volume increases, the temperature also increases. So as the temperature increases, the gas volume increases. Increase in temperature will increase the gas volume. Volume of gas will be increased as the temperature increases. So this is the main effect behind the temperature and the pressure. As the temperature increases, the gas volume increases, the density decreases as the volume increases, so the balloon rises. So by increasing the temperature, the volume of the gas increases and density decreases. Now the particles that are present in it are less dense. They are less dense just because of less density, the balloon rises up. If a gas is stored inside a container that is squeezed, the pressure increases as you decrease the volume. This is what happens also in the bicycle pump. So you can take the example of both of these. As you compress the bicycle pump, the high pressures allow you to inflate a tire, and you can feel the force of high pressure if you put your finger on the end of the pump. So these are the two examples related to the pressure and the temperature. Next, I will talk about the gases and the kinetic theory. Gas particles are in constant motion or the random motion, and the pressure that a gas creates inside a closed container. Here, suppose this one is the closed container of any gas. Gas particles are present here. These are the gas particles, and gaseous particles are in constant and in random motion. The pressure that a gas creates inside a closed container is produced by the gaseous particles hitting the inside walls of the containers. These particles are hitting the walls of the container, and then pressure is produced because of the moving particles of the gas or the colliding with each other and also with the walls of the container. The particles that are present in the gaseous state or in gaseous particles, they are colliding with each other and also with the walls of the container. So by increasing the temperature, it increases the kinetic energy of each particle. When the temperature increases in gas particles, then kinetic energy increases. So when kinetic energy increases of the gas particles or each particle that is present here, this is the thermal energy from increasing the temperature that is converted to the kinetic energy. So as the temperature increases, particles move faster and they spread out. Kinetic energy is due to the motion. So when kinetic energy is produced, they move or spread out more faster. So the gas particles, by increasing the temperature, they move and spread out more. If the gas particles are inside the container, they collide with the container walls more frequently. If the container walls are flexible and stretchy, then the container will get bigger, just like the hot air balloon. So this one is the effect of the gas particles and also of the temperature on the gas particles. So next I will discuss about the how does the pressure will affect the volume of the gas. Effect of pressure Now we will see the effect of pressure on the volume of the gas. Pressure is about the number of the particles that are present in a given volume. For example, this is the container, and this is the pressure that is applied on this container. We have gas particles that are present here like this. These gas particles collide with each other and also with the walls of the container like this. Gas particles are always in the random motion. That's why these molecules collide with each other or also with the container walls. So what will happen when we increase the pressure? When the pressure will be increased, the upper arrow, as you can see here, this is for the increase in pressure. P is for pressure. So after increasing the pressure, then pressure increased means, now you can see here this one. Moving the piston towards the downward will increase the pressure. More frequent collisions will happen here, and gas particles will collide with each other more frequently. More frequent collisions of the gas molecules when we increase the pressure and also with the walls of the container. So when pressure increases, by increasing the pressure, this is the main point, the volume decreases. You can see here the volume decreases. That means the molecules collide with the container walls more frequently. Since the volume is decreased, the gas particles hit the container walls more frequently, and if pressure is too high, then this can result in the container of the leaking gas or maybe the exploding of any container if too much pressure is increased in this case. So this is the effect of the pressure. As the pressure increases, the volume of gas decreases. Pressure refers to the number of particles that are present in a fixed volume. So by increasing the pressure, that will decrease the volume of the gas, and as the gas particles are forced closer together, so by decreasing the pressure, it will increase the volume of the gas, and as the gas particles can spread further apart. So this is the effect of the pressure by increasing and also by the decreasing. This is the main point about this. If we increase the pressure, then the volume decreases. Why volume decreases? Just because of that. Volume pressure refers to the number of particles that are present in the fixed volume. Increase the pressure will decrease the gas volume because the gas particles are closer together. When they are closer together, then the volume decreases. Closer together. So this is the main point about the effect of pressure on the volume of a gas, and as the temperature increases, then volume increases. As you can see here, by increasing the temperature, the volume increases. Increases the temperature will increase the kinetic energy of the gas particles, so the gas particles will move and collide with the container more quickly and spreading further apart. So by increasing pressure, volume increases, and by increasing temperature, then volume. By increasing the temperature, the volume will increase. Why the volume increases? Because the kinetic energy of the gas particles that are present here will collide more, and they move apart more randomly with the container more quickly, spreading further apart because of increase in temperature. So by increasing the temperature, there will be more volume or increase in volume in this case. So the next one is the last topic which we will cover today, which is diffusion. This one is the last topic of today, and in diffusion, first of all, I will tell you about the definition. Diffusion mostly occurs in the gases and in the liquids. Diffusion occurs in the fluids, not in the solids. So in fluids we have gases and liquids. Gases and liquids are included in the fluids, so diffusion happens just in these two states. This is just because of the random motion of the particles. Random motion of particles. In case of solid, particles just vibrate at their fixed positions. They don't have any random motion, so just because of that, diffusion does not happen in case of solids. Diffusion will happen in case of the fluids like the gases and the liquids. Diffusion is where the particles move from an area of high concentration to an area of low concentration, like you can see here this one. If we have any container like this, and this container contains some particles that are of, one second, this container contains the particles of the potassium manganate, right? Potassium manganate is of purple in color, this one, like this. When we add the potassium manganate in a water, this container is full of water, this one, H2O or water is present here. So when we add potassium manganate, which is purple in color, into the water, so diffusion happens where the particles move from an area of high concentration to an area of low concentration. You can see here water is present in this container, but if we talk about the potassium manganate is present in just here, that is in the concentrated form in the bottom of the container. So eventually the concentration of the particles are much higher at the bottom of the area, like the potassium manganate particles. So diffusion will happen here. The particles will move from this area to the area where they are present in the low concentration. For example, I will tell you like this. These are the two different sides of the container. In the center we have a membrane. From this membrane some particles can move towards the left and some can move towards the right. So what happens here, this one, on the left side you can see here there are more particles, and on the right side we have just 4 particles. You can say that this is the area of high concentration area, and on the right side we have the low concentration area, or the particles are present in low. So what happens in the diffusion is the particles move from an area of high concentration towards an area of low concentration, like this. So the particles will move from left towards the right, from an area of high concentration to an area of low concentration. Eventually the concentration of the particles is even, as the particles are evenly spread throughout the available space. So diffusion happens on its own and no energy input is required for the particles to move from an area of one concentration to an area of another concentration. It occurs faster at high temperature because particles have the more kinetic energy. So if we move towards this example, potassium manganate particles will be dissolved in the water like this. When will they dissolve? They dissolve just because of that they are present in high concentration, and the concentration of the particles is even, as the particles are evenly spread through this available space. You will see now what happens after some time, like maybe after 15 to 20 minutes. The particles will spread from an area of high concentration to an area of low concentration, like this is the container that contains potassium manganate particles here. So after some times the particles will move here. After some times it will move upward and upward. So we have the concentration here. They are more concentrated particles are present at the bottom, and they will spread or diffuse through the solution from a region of high concentration to a region of low concentration. After some times, maybe after 30 minutes, now we have the solution that is purple, or you can say that the purple the color of the water will be purple or pink after maybe 30 minutes or 1 hour. The concentration of particles now evenly spread throughout the solution, and potassium manganate solution after 30 minutes will we can say that now equilibrium is reached. All the particles are evenly spread through that liquid that is present between them. So this is the diffusion of the potassium manganate, KMnO4. This is the formula of potassium manganate, and the color of the potassium manganate is purple or purple to pink color, and the color of the water is water is colorless, so potassium magnet will diffuse in the water. After a few minutes, the concentration of the KMnO4 is same throughout the solution, as you can see here. Here the concentration of all the potassium magnet is same, so diffusion happens like this in case of liquids. Next, we will move towards the diffusion in the gases. Now we have to move towards the gases. Diffusion is faster in case of gases than the liquids. Faster than liquids. So diffusion is faster in gases than in the liquid. This is because the gaseous particles, you know that the gas particles have more energy and they move more randomly and quicker than the liquid particles. So diffusion of the, if we took the example of the bromine gas into the air, like you have any cylinder. So in case of gases, the diffusion of the bromine gas, will take the example of the diffusion of the bromine gas and the air. Like in a cylinder, we have air that is present here and bromine gas, Br2 bromine gas. So after some times, bromine diffuses until it is evenly spread. The bromine will diffuse into the air just because of the diffusion, and bromine diffuses until it evenly spread throughout the container. At the start, the orange brown color bromine is present in the form of the orange brown bromine gas that is in high concentration in the bottom of the cylinder. It diffuses from a high concentration towards the low concentration. So after 5 minutes, what will happen? The bromine gas will be diffused from the bottom jar until it is evenly spread through both the jars. The same can be said for the air, although it is less obvious that it is colorless. So for air, it is less obvious just because air is colorless, but bromine is in the form of the orange or the brown color. So after some times, we have the even concentration of both. Here all will be orange or brown in color just because of the bromine gas. So you can say that after some times, bromine is evenly spread and the color of the whole cylinder will be orange or brown. So this is the diffusion of the gases. Gases diffuse much faster as compared to the liquid because gas particles have more kinetic energy, they have more random motion. So this is all about the diffusion into the gases and also in the liquids. Next, I think we should move towards another example of the diffusion of the ammonia and the hydrogen chloride gas. So this one is more important. This question may appear in the exams also. So diffusion of the ammonia and the hydrogen chloride. Ammonia gas and the hydrogen gas react with each other. Ammonia, NH3 and HCl, both are present in the form of the gas, right? So when both are present in the form of the gas, they react with each other to form a solid that is known as the ammonium chloride and H4Cl. They both react together and the molecular mass of the ammonia is 17. 17 is the molecular mass, and the molecular mass of hydrochloric acid is 36.5. So this is the main difference between these two. This means that ammonia will travel faster and further than the hydrogen chloride gas. Like this is the cylinder. This one is the cylinder. In this cylinder we have a cotton. This one is the cotton that is soaked with the ammonia solution, because this one is in the gaseous form, or we put the ammonia gas into the water or any type of liquid to form a solution, then we soak the cotton, and cotton wool soaked with the ammonia solution is put there in this cylinder, and on the right side we have the cotton wool with the HCl that is soaked in the concentrated HCl. So After some times, ammonia react with the hydrochloric acid, making the product, that is ammonium chloride, that is closer. So after some times, what will happen? Ammonia will move towards the right and hydrochloric acid will move towards the left, just because to show the reaction between the both. So you can see here, this is the solid ammonium chloride, NH4Cl will be produced here. Ammonia molecules have less mass as compared to the hydrochloric acid molecules, so they diffuse faster and the product forms closer to the HCl, and just because of the less mass of the ammonia, ammonium chloride will be formed nearer to the hydrogen chloride. This can be seen as the smoke ring that is formed inside the gas tube. So that is the difference, or that is also the difference between the different gases. Different gases have different molecular mass. Ammonia has the molecular mass of 17 and HCl has the molecular mass of 36.5. So just because of the difference in their masses, ammonia will travel faster and further than the hydrogen chloride gas. Therefore the ammonium chloride will be formed nearer to the hydrogen chloride. So that can be seen here as a ammonium chloride NH4Cl. Ammonia reacts with the hydrochloric acid, making the product ammonium chloride, that is closer to the HCl of the end of the tube. So this is all about the first chapter, which is about the states of the matter. If you have any question or any confusion, you can ask in the comment box. Okay, we will see you in the next video.